Have you ever stopped to think about the invisible world that's all around us? The world of energy and matter. Today, we're going to pull back the curtain on the hidden forces that decide why water is wet, why ice is solid, and why steam is, well, steam. Let's get into it.
It all kicks off with a really simple question, one you might not have ever considered. Why is water a liquid when you pour it? But methane, natural gas, is a gas. I mean, they're both really small molecules. So what gives? What's the big secret?
And when you look at the numbers, the difference is just staggering. Water boils at a nice, familiar 100 degrees Celsius. Methane boils at a mind-bogglingly cold -162. That enormous gap is the puzzle we're going to piece together today.
To figure this out, we're going to build our case step by step. First, we'll cover the absolute basics of energy. Then we'll look at the three familiar phases of matter. After that, we'll dive into the secret forces between molecules. And finally, we'll see how it all clicks together when matter changes from one state to another.
All right, let's start at the beginning. Section 1, energy. You can really think of this as the engine that powers literally every single change in the universe. So what is it? Well, the scientific definition is actually super simple. Energy is just the capacity to do work. That's it. Whether you're lifting a heavy box or your own heart is pumping blood, that's energy doing work.
And energy pretty much comes in two main flavors. First, you have potential energy. That's stored up energy. A great example is the water held back by a dam. It's just sitting there waiting. Then you have kinetic energy, which is the energy of motion. So when the floodgates open and that water rushes out, its potential energy has been converted into kinetic energy. And that brings up the golden rule, the law of conservation of energy. It basically says you can't create energy out of thin air and you can't destroy it. You can only change it from one form to another.
So, how do we measure this stuff? Scientists use a couple of key units. The first is the calorie, and pay attention, that's a lowercase c. A calorie is just the amount of energy it takes to heat up 1 gram of water by 1 degree Celsius. The other common unit is the joule.
Now here's where it gets relevant to our daily lives. You know the calorie you see on a food label, the one with a capital C? Well, that's actually a kilocalorie. That means one of those food calories is equal to 1,000 of the little scientific calories we just talked about.
And this explains why different foods give us different amounts of energy. Proteins and carbs give you about 4 calories for every gram. But fat packs more than double the punch, with 9 calories per gram. It's just a much more energy-dense fuel for our bodies.
Okay, so we've got a handle on energy. Now let's connect that to the very state of matter itself. We're talking solid, liquid, and gas. And it turns out, the amount of kinetic energy that particles have is what determines which state they're in.
In a gas, the particles are just buzzing with kinetic energy. They're flying around really far apart from each other. In a liquid, things have calmed down a bit. The particles are much closer, and they start feeling some attraction to their neighbors, but they can still slide past each other. And then in a solid, the particles have very little kinetic energy. They're basically locked into a rigid, organized structure, just vibrating in place. You can see a really clear trend here. As you go from gas to liquid to solid, the density skyrockets, the particles slow way down, and the interactions between them get much stronger.
And that idea of stronger interactions brings us to the absolute key to this entire puzzle, the forces between molecules. You can think of these as an invisible glue holding matter together. And the strength of that glue, it changes everything.
These are called intermolecular forces. And just to be super clear, these are the attractions that exist between different molecules, not the bonds inside a molecule. The strength of these forces is what ultimately determines a substance's physical properties, like its melting point and its boiling point. There are 3 main types, and they get progressively stronger. The weakest are called London dispersion forces, and the key thing to remember is that all molecules have these. A step up from that are dipole-dipole interactions. These are stronger, and they only exist in what are called polar molecules, molecules that have a permanent positive end and a negative end, kind of like tiny magnets. And then you have the heavyweight champion, hydrogen bonding. This is the strongest type by far, a special kind of super attraction that only happens when hydrogen is bonded to nitrogen, oxygen, or fluorine. So let's do a quick recap. London forces are weak, but they're everywhere. Dipole-dipole forces are in the middle, and you only find them in polar molecules. And hydrogen bonds are the super strong ones, but they're exclusive to molecules containing OH, NH, or HF bonds.
All right, we're in the home stretch now. Let's put everything together. This is where energy and intermolecular forces have their showdown,
and explain how matter transforms from one state to another.
So if you want to break apart those intermolecular forces and move to a state with more energy, you have to add energy. It's really that simple. Melting a solid into a liquid or boiling a liquid into a gas, both of those processes absorb energy. And the reverse is also true. Freezing and condensation release that same energy back into the environment.
The specific amount of energy you need to melt something has a name. It's called the heat of fusion. For water, it takes almost 80 calories of energy to melt just a single gram of ice.
Okay, but check this out. The energy it takes to turn a liquid into a gas is called its heat of vaporization. And for water, that number is a massive 540 calories per gram. This incredibly high value is exactly why evaporation is such a powerful cooling mechanism. It just takes a ton of heat with it when it leaves.
We can actually visualize this with something called a heating curve. The diagonal lines are where the temperature is rising as you add heat. But see those flat sections, the plateaus? That's where the phase change is actually happening. Even though you're still pumping in heat, the temperature stays totally flat because all that energy is being used to break the intermolecular forces, first during melting and then again during boiling.
And this explains a feeling we all know very well, sweating. As that water evaporates from your skin, its incredibly high heat of vaporization means it's pulling a huge amount of heat away from your body. That's what's actually cooling you down.
And with that, we have solved our mystery. The answer is hydrogen bonds. Water molecules form these incredibly strong hydrogen bonds with each other. Methane, on the other hand, is a non-polar molecule, so it only has those weak London forces holding it together. You have to pump in way more energy to break water's powerful bonds, and that is exactly why its boiling point is over 260 degrees higher than methane's.
So the next time you see morning dew on a leaf or watch a puddle evaporate on a hot day, you'll know the powerful, invisible forces at work. So my question for you is, what other things in your daily life can you now explain just by understanding the quiet strength of these intermolecular forces?